Yeah, thanks very much for that, Prof. Mostert. Yeah, what I was doing was trying to open the debate really on the back of Prof. Knudsen's presentation and your presentation, Prof. Mostert. And I have got an unstable internet. And what the question is, given that it's quite difficult to get funding for research unless people see it sexy and attractive and new, how do you think we can try and get the same sort of research interest and money and support for looking at steels, which are still really, really important materials? I mean, they can really help us out of the energy crisis. So what I'm asking from both Prof. Mostert and Prof. Knudsen is, have they got any suggestions as to how we can package this to try and flag this to the people who might help us get money so that we can get money? Thanks.
Right. Yeah, I can perhaps just start by expressing my frustration in this regard as well. So we've got a situation in South Africa that there are very ambitious plans for the green hydrogen economy, and the type of monetary values mentioned in those plans and white papers are huge, but fundamentally the country needs the type of testing equipment that you need to evaluate the influence of hydrogen on the material. So as I indicated in my talk, the transportation of the hydrogen is going to demand that we have a particular testing program in South Africa. The storage of hydrogen under pressure will also require that because there is particular stringent regulations regarding vessels that are storing gases under high pressure, especially if it's now an explosive gas that is stored. Testing will be required. But there's nothing in the country that can specifically perform these tests under high pressure hydrogen, where you can simultaneously then strain a material. And it appears that the aspect of the hydrogen steel interaction has been largely ignored in the planning to date. And obviously that's going to catch up with us. So from my side, I've knocked on a couple of doors regarding funding for this. Unfortunately, it's a type of funding that's not normally available to universities. It is in the order of, say, 10 million plus that you need here, without much success. So to answer your question directly, I don't have any good ideas at this stage in terms of accessing that type of money, but we will persevere, and at some stage somebody is going to see that they need this type of testing and equipment. Thank you.
Thanks for that, Prof. Mostert. I was just wondering, we haven't got that sort of money either, but I was just wondering if we could use some of our current funds to try and get together a meeting and invite people, whoever you think from industry and government, and whether the NSTF could help as well, and run a little discussion or little workshop on it. Would that help? Thanks.
Yeah, I think that's an excellent idea. So there are a number of industrial players in the field and clearly the national structures in terms of DSI and the like also have a stake in this regard. But my experience to date is that nobody really wants to take the lead and fund this on their own. So I think that is a very wise type of approach to get something going where everybody chips in, and then the amount becomes reasonable for everybody concerned. So that is something we can look at, and I'd support that fully from my side.
Thanks for that. Then maybe we can start the first meeting going, and you will hear from us. Prof. Knudsen, have you ideas how we could try and keep the keep the research occupied like we used to in the days when 3CR12 was still being looked at?
So, sorry, Leslie, was that a question?
Yes, it was. I've got horrible internet. I was asking you if you've got, taking your talk into account, which was excellent. Thank you for that. I was wondering if you've got any ideas how you could possibly get an initiative going, which was doing what was happening with 3CR12 and making sure that we had enough researchers to fill up the missing middle. Thank you. So it's sort of a way forward. Thanks.
Yeah, I mean, the difficulty at the moment, of course, is unlike the days of Middelburg Steel and others, Eskom is in a very, very precarious position. They, I actually spoke I interviewed a few of the engineers about 3 weeks ago, and they really don't have the capacity to be able to walk out of their station. They're fully focused on literally trying to keep those plants running. So they're in a very difficult position at the moment. We almost need a sea change. We almost need somebody at senior level at Eskom to say, okay, guys, we'll keep doing what we are doing because we've got to fight like crazy to keep this plant going. But let's separately try and build expertise, which, as I say, will come at cost. But eventually, it should have a payback. The other thing is that government and the National Research Foundation need to recognize this. I mean, my first-hand experience of 3 years back, I put as a rated researcher, I put in an application for a funded project for doing exactly this kind of work. And the response I got was, excellent project, we should support it, but we got no money. So I put it back in again the following year, and I actually got back exactly the same letter, but with a different date on it. And at that point, I thought to myself, what's really happening here? So you know, they really need to recognize that it's also about sustaining ourselves, and sustaining ourselves is about making sure that we have enough research on the go that keeps a good base that can keep things going, like power plant and pipelines and refineries and everything else. It cannot only be focused on novelty, because, as you know, novelty takes a very, very long time to reap any rewards. And I'm sure if you did an analysis on the government spend on novelty versus the return, it would be very, very, very low. Now, of course, first world nations, you've got to, once again, you've got to splash out and make that investment. You've got to take that risk. But you've also got to make sure that the other things are working. And unfortunately, we've dropped the ball on things like basic physical metallurgy knowledge, particularly on a big company like Eskom. So, Leslie, I don't really know what the short answer is. Eskom is re-engaging with universities again to get contracts sorted out. So maybe we can, once this, in about 6 months' time, I can revisit where they're going to put the new contract for material science, and maybe we can start talking to them about developing some form of a network. But the company must be embedded in this, otherwise it won't work.
Thanks for that comment. Has anybody else got something to put into this part of the debate, please? Thanks.
Leslie, can I ask Michael a question?
Please do. I was just trying to get this thing started.
Yeah,
okay.
Michael, thanks so much for your presentation, which I really enjoyed. I was just looking at the sort of density wins, and I guess they are significant, I guess, but of course not substantial. The question I really wanted to ask you is, when you look at that pie chart of yours, which shows the cost of the component versus the cost of the hospital and the cost of the medical practitioner, the cost of the component is substantial. But I just wondered what proportion of that cost of the component is the manufacturing of the component versus the material cost. Because titanium is more expensive than steel, but it's not that much expensive. So I just wondered, if you produced a lower density stainless steel that did the job, do you really think that the cost of the component will come down substantially?
Yeah. Thank you so much for that question. I have a feeling that the cost of the component should be cheaper than that of titanium, because we all know that titanium is expensive, not only in terms of extracting it from its ore, even forming it into different shapes and of course machining it and all that. We've made a lot of progress, in recent years to bring down the cost a bit, but it's still not as cheap as iron. So so the pie chart that I showed actually was giving an overall cost in terms of producing the component itself. So it caters for the cost of the material, the alloying element, the base material alloying elements you had, and manufacturing. There's no way that I would like to think that there's no way that the cost of processing there wouldn't be a significant difference between the cost of processing titanium and low density steel, because iron is still the base material in the low density steel. It has higher percentage in that. We could have up to 60% of iron, and that's really cheap compared to when you develop titanium alloys, for instance, that would have 80 or 90%. I think that in terms of cost, we still beat titanium. In terms of the density, yes, it's not like it's a lot that we can achieve, but I've seen a study where they reduced it to about 5%, but the properties are not that great. We also saw that in our trial runs, but if we could go from 8 grams per cm cube to 6, that's quite substantial. And there are lots of new processing methods coming up now and we know that steel is very stable and amenable to different processing methods. I think most people are now even developing porous titanium alloys to address the elastic modulus question and all that. All these we can subject this low density stainless steel to. And I think in the long run, it will still be cheaper than titanium. I don't think it would outperform titanium in terms of biocompatibility, overall biocompatibility, but at least it provides alternative material to titanium if you can afford titanium. Currently, I mean, they use 316 stainless steel. That's very heavy, and that causes stress shielding problems. So if we could reduce the density a bit, we know that in terms of cost, it shouldn't be as expensive as titanium. So there seems to be some promise in there. It's still it's a new area. It requires maybe we still need to work on this for the next decade to be able to see if we would get something meaningful out of it. But the signs that we are having from the little results we've gotten seem to be promising. I hope I've managed to convince you, Prof. Thanks.
Thanks, Mark.
Thank you. Thank you for those comments and questions. We do have another speaker in the audience. So what I'd like to do is introduce Paverga Jabu, and the talk will be titanium oxide nanochill film decorated with beta gallium-2 oxygen-3 nanoparticles for enhanced water splitting properties. So please take over and run the presentation. Thank you.